you don't finish right now, that's a great resource for you for later. As we kind of wrap up the first part of this unit, the second part of this unit, atomic structure, photoelectron spectroscopy, light, and light matter interactions, that was all kind of like part one of this unit, okay? So part two is all bonding. What are some things that you probably think from your reading so far? We're going to be talking about. Riley, tell me something you think we're going to be talking about. Okay, and we're going to talk about that basically today and a little bit more in like a week or two, and that's it for metallic. Courtney. Okay, so network covalents like diamonds, okay, and graphite, and a couple of other things that really are just carbon-based. What else? Sean?
Covalent.
Covalent, and that's like the world that we live in most of the time. We talk about the covalent bonds, how we draw the Lewis dot structures, what kind of shapes do they take on, what are the bond angles, how do they bond, atomic orbital theory versus molecular orbital theory, and then all the properties they take on with intermolecular forces. That is a huge component, okay? Kurt?
What makes things conductive?
Okay, so the activity of electrons and or mobility of electrons and how that can be translated to conductivity. Jacob?
Ionic bonds.
Okay, in ionic we did a lot with yesterday. We talked about lattice structure and lattice energy already. We're just going to kind of tie the last two pieces together today, and we're basically done with ionics. Outside of that last column you guys were reading was everything about what? Properties. We will be talking about physical properties galore, like who has a high melting point, who has a low. Why does one thing vaporize while something else doesn't? Why is iodine a dang solid and it's a halogen with all the other halogens, but why is I2 a solid, bromine's a liquid, fluorine's a gas? So the properties are the qualitative side of things that we're working with so much. So why do you think I'm having you guys read? It's a lot of like content to take in and then verbalize and practice, okay? So as a form of verbalizing and practicing, come back to the last stations. There are the purple baggie and blue baggie. You want to mix up the purple baggie and blue baggie. After about 10, you guys have 5 minutes to organize those into categories. You'll see it when you see it. I'm about 10 to do a work for do not get the pieces mixed up. I counted them. You cut them out and all that jazz. Here's another one, there's another one. If you're working up to chairs, more than that. The two of you come on this side. Look for the headers first. Look for the headers. It's basically like a graphic organizer. If I were to start with one, listen up. If I were to start with one, I'd start with the blue one. The blue one is the easier one, and then you're going to move on to the purple one. Get your right organized first.
I'll just do it till later, like 6, including the title. There's a little to
Yeah.
don't protect electron share. That's just okay, I didn't think so. But do you not only be eating those? Oh, okay. Well, I just put it there because I was
Take one more minute, guys. One more minute.
yeah. This. Why do we
I feel like I'm not supposed to have 30.
Yeah, it's not good.
Alright, pause. 3, 2, 1. Alright, everybody look at the purple columns. Let's go in order and let's just see what we put there. I'm under my single covalent structure. So let's start with something more familiar. Let's start with ionic. Starting with ionic. Tell me something you guys put. I'm gonna go in order. So Rushi's group and around. Okay, so Rushi, giant ionic structure, purple. Can you please be louder? Regular crystal arrangement. Check. Make sure you guys are listening because I'm not screaming for you. My voice is not Next. Second part is an example. Next.
Strong electrostatic attraction between positive and negative ions.
Beautiful. Next. Picture. What's the picture look like?
Negative and positive ions.
Negative and positive ions. So the dark color and like a gray and positive. Okay, great. Next. Be more specific. So yes, so that one does not belong in. So ionic is very peculiar. It doesn't conduct electricity all the time. Only when molten solution. Thank you. Next. Pinky. Nope, that's not ionic. So we are in the ionic category, right? Graphite is not an ionic compound. That's a network of ions. Next. Okay, good. High melting points. Almost all our solids are temperature. Oh no. Less. Always solid room temperature. So ionic is always lighter temperature. The one that is almost all solids are almost all solids are temperature belongs to what category? Metallic, because there's one metal that's not solid. Anybody? Very green. I'm making sure I'm orderly doing this with you, so if you can't hear me because you're talking, then you're losing out, okay? So the other one that was a regular 3D arrangement of positive and negative ions, that should belong in ionic. I think that's it. Okay. Let's go to metallic now. Metallic, so I'll start. Positive ions surrounded by a sea of delocalized electrons. Savannah, your group next. Metallic one. Mally will next. Thank you. Conduct electricity with no limitations, right? It's going to conduct electricity. Next. Beautiful. Next. That's what you just said. Always was with ionic, right? No, that's right. There's one says always and one says always. If you have, make sure you at least have it because some of my honors cam don't organize very well. Alright, so no, hold on, pause. There are two. One of them goes in network covalent. I'm sorry, I did forget one network covalent. Alright, so backtrack. High melting point. Almost all are solid, thank you. Next. Regular crystal arrangement. Yes, because the metallic structure is it called a lattice. So am I going too fast? Okay? No response. Okay, great. You said that. Sodium's a good example, thank you. Next. Little tiny dots with the electrons around. Tiny dots, okay. And then the last one says strong attraction between ions and delocalized electrons. Those are the cations, and then the delocalized electrons are there as well. So if I'm ionic and metallic taken care of, let's go simple covalent. I'll start simple covalent picture of methane. Picture methane. Next group. That's you, Samantha. Nope, we're doing simple covalent. Simple covalent.
Strong bond between atoms and electrons.
Strong bond between atoms, electrons are shared. That's the definition. Good. Next group. Don't collect. Yes, no, there is nothing that's ever going to connect electrons. We're going to put down a single electron. Next. Beautiful. Thank you. Next. This is your same example. Iodine. So they have iodine under the single covalent. Anything else? Next group. Hold on. I can help out. Yes, isolated molecules. So when I main feature network covalent. Diamond is an example. Good. Jacob.
Most of the electricity is like that.
Yes, graphite is one exception. Has sheets that allow electrons to bounce up. On the next picture of that like huge crystalline structure, a huge continuous structure like a blob structure. Okay. An answer. Yes, and these are network covalent structures. This is the one difference, huge difference between covalent and network covalent. Covalent are what generally refer to, let's say, gas or negative. Network covalent structures are huge structures, but they're all solid. So like a huge silicon disk with a solar panel in it is a giant covalent structure. Quartz, rocks are giant covalent structures. Sand, silicon dioxide, it's teeny tiny, but it's a solid. So these are always solid. Next group, we're on. Good. And then last characteristic. Do you guys have strong bonds between atoms, electrons are shared? I think that was in most people's slides, right? Okay. Anything else? Let me try. Okay. Put those back in the baggie. Let's go, guys. Back to the baggie. Okay, we said that was simple. Please put them back in the baggies. Oh yeah, can you take a picture of it? Take a picture of it. I will find another one. I don't have it. Alright guys, I'm gonna go back to your seat for me. We're gonna chat for a little while about some of these properties we learned. On your way back to your seats, please put your FRQs in the box. I'll give them back to you tomorrow, hopefully. I want to see the limitations first before I start going over them. It helps me focus which ones I can do with you. FRQs in the box, back to your seats. Here's the bucket. I'm trying to video this for like this too. Alright, FRQs in the box, guys. Thank you. And then guys, pull out your PES stuff. We're gonna check that one fast before we move. Trying to wrap up some loose ends here. I'm gonna check over those last 4 PES ones now. Contact loose ends here on some of the old stuff. So FRQs in the box. Oh, sorry, PES. Thank you. Alright, so those of you who PES out, go ahead, tell me what you guys got for 4A, which was the one with an answer choice. Jacob? Okay, we said A. Why? Go for it, Courtney. Give me an explanation.
Because the little, what do you call that?
Peak.
Yes. The peak or potassium,
When you say higher, what do you mean?
it's more intense than greater.
That has nothing to do with what you're answering though.
So,
Hold on, pause. Guys, what does the intensity peak represent? Number of electrons, right? So this has 2 electrons in its 3s peak. Well, that makes sense because it's 3s2, which is what potassium has surpassed the 3s category, right? So it's filled up. And then sodium only has a teeny tiny peak, meaning half of that, right, in size. So that's got 1 electron in it, and that's because sodium has a 3s line, because that's where sodium stops from the group. So, okay, intensity means electrons, electron count. Go ahead, Courtney.
yeah, so then, K has a greater than 2 because, if you look at the
Okay, so between them, the only difference that will make a difference in binding energy of the 3s orbital will be the strong pull of the protons. So the nuclear effective charge is greater, therefore binding energy is higher for potassium than for sodium's 3s orbital. Thank you. So A should be the correct answer. And why would B be ruled out? Go for it, Levi. Why would B be ruled out? Well, that's valence electrons, but we're talking about, in this example, it talks specifically about 3s. And we just said in this one there was 3s2 because potassium's lower, and sodium is 3s1. So it's not that, but there was something else. Why is that wrong? According to the data. Or Kurt can help you. Pass? Okay, Kurt.
Because that would make A have a lower sodium.
Right, so B contradicts the data. So you always have to reference the data. If the data is showing you something and then you see a correct answer, sure, maybe potassium does have more electron-electron repulsion in the 3s because it's got 2 electrons versus sodium with 1. But the data doesn't say that because it would have, with electron-electron repulsion, your 3s binding energy would be much lower because it would be an unstable arrangement. So it has to agree with the data. Thank you. 4B, we kind of just mentioned what this meant. Peak size differences relate to 2 electrons versus 1. This didn't have an answer choice though, I don't think. Okay. 5, look at this one. Maybe this front table up here, Avery's group, tell me what you guys put. Louder. D as in dog. D as in dog. Okay, so D as in dog, let's see here. Can I get a poll? Who else put D? Most of us. Okay, so were some other options here that we selected? Yeah, you put A. Okay. All right. So anybody else want to volunteer an answer? Okay. So true statement. Likely, oxygen has more valence electrons than titanium because if you look at oxygen, we have 6 valence electrons versus titanium, which only has like 2 or 4, based on how you're looking at it. And carbon only has 4. So that is a true statement, but that has nothing to do with the secondary part of that statement. Okay, absolutely nothing, because in this case, we're referencing different pieces of these atoms. We're referencing the 1s of oxygen, the 2p of titanium, and the 1s of carbon. Well, that's going to make some differences across the board because we can't have a solid comparison. So who wants to explain this for me? Avery, your D is right. You want to explain it? Oh, so long ago. Okay, so I'm reading Avery's mind, and she says, comparatively, oxygen versus titanium versus carbon. Oxygen has how many protons? 8 protons. Okay, titanium? 22 protons. And carbon? 6 protons. If you're not like annotating your diagrams to give you some perspective, it's really hard to hold all that in your brain and actually see the comparison. So I can obviously see that titanium's got a huge effective nuclear charge compared to these guys. So that's kind of one thing to think about. And then separately, I can see that the 1s orbital of oxygen has a higher binding energy because it's closer to the nucleus, as we kind of portray. But it has a high binding energy. That's because it's the 1s electron, right? 1s orbitals undergo nuclear penetration, so they have a very strong attraction for their nucleus. Not because it's got 8 protons, but because it's staying close to the nucleus, right? Well, these 2p electrons, yeah, they're farther away from the nucleus, but that nucleus is really very strong, has a high Zef. And this again is the 1s electron, 1s orbital undergoing nuclear penetration. So why is oxygen's here and carbon's here? Why does carbon have a lower binding energy for its 1s electrons? Vicky? Skip? AJ? Or Zef, right? Higher Coulombic attraction or Zef. If you see the same energy level, oxygen and carbon on the same energy level, you've got 8 proton Zef versus 6 proton Zef. You're talking about the 1s electrons and 1s electrons. Everything else is the same. The only thing that's different is the nucleus. It's Zef. That's why 6 protons is not pulling as harshly on this 1s orbitals, so it's got a lower binding energy. than oxygen's does, higher binding energy. But, so you can see all these comparisons up here, but then when you start reading, you should immediately start knocking some of these questions out. This is like nonsensical. The first statement's right, maybe even the second statement is right, but they don't relate, especially nor even do they correlate to the graph. Oxygen's more electron to electron repulsion. Yeah, true statement, but we're not even referencing 2p of oxygen, so how could we compare the data? Because we might have more electron repulsion because we have 4 electrons in p, but who cares? It's not in the data. Titanium atoms are present has nothing to do with this graph, right? If anything, that might be like a mass spectroscopy graph versus a photoelectron spectroscopy graph. Greater electron nuclear charge, check, but the 2p sublevel experiences greater shielding. True statement? Yeah, because what's between the 2p and the nucleus of titanium? 1s and 2s, right? So there is more shielding than the first sublevel. So all that's true, and it agrees with the data the way it works out. Because this has more shielding, so it's going to have a lower binding energy associated with it. So these graphs can tell you a lot of information. I just don't want you guys to miss out on the little details. All right, last one. This gives us a transition metal of scandium or scandium. Commonly makes a 3+ charge opposed to a 2+. Volunteers some answers for me? C. Who else? C. Anybody else? Okay, so I'm sure you label this for yourself. Can you label your peaks for me? What is this? 1s2, okay. 2s2, 2p6. You can see it's 3 times the size. Keep going. 3s2, so the same as those other 2s, and then 3p6, and then what's this inside one? 3d1. That is 3d1, because do you see the scale? It's probably really difficult to see on your paper. The scale of that is different. That's a single and that's a double. So the first peak here is actually 3d1. The second peak here is what? 4s2. I know when we do our electron configurations, we go 4s2 and then 3d1, but the reason why we drop in energy levels is, when we hit 4s2 then 3d1 is because they are very, very close according to Alfvé's diagram, and energy in itself. That also relates to binding energy. So because these 3 electrons are all very narrow in their energy spectrum, you can easily take all of them to create a 3+ charge for scandium versus just the 2 electrons. It actually is just very minor in their differences in their binding energy. Okie dokie. So how do we rule out these? Removing 3 releases more energy. Does it release energy when it removes these? It requires energy to kick that the electron out with the kinetic energy, right? So I wouldn't necessarily, it says it releases more, plus you don't have that kind of information. You only have binding energy, you don't have releasing energy. You don't have like electron affinity or anything like that. Lose the number of electrons that will result in noble gas. Possibly a true statement, but doesn't indicate anything about why the 3D is going, because actually if you lose the 2s electrons, doesn't that result in a noble gas electron configuration? Because you back basically up to a full 3s2, 3p6, that's a full electron configuration of octet, so that's not a true statement all the time. Removing 2 electrons alleviates the spin repulsions, emptying the 4s completely. They're not actually repelling each other so so much, because that's actually a full subshell, so it's a fairly stable arrangement. So C would be the best answer there. Okay, so pulse PES stuff for a little bit. Let's chat about, you guys tell me, I was looking back at the free response practice or stuff from the ask-based test, and I sat down and talked to a lot of people about question 1, which was the big, huge question, and I had some people who still left some things blank or had some misconceptions. Do you guys want me to go over that today or like just later? I'm trying to tap some loose ends, but I also know that we need to progress as well. So let me pause, and I won't do that today. I'll do it later. All right, so if you want to stand up for this, my tired people, go for it. But I'm only going to hit the highlights of ionic. Please add this to your annotated notes. So whatever you had from yesterday. And the stuff in red is anything I would consider more important than other things. The whole class gets ups and stands. Okay. So I'm going to write down some Lewis dot structures and do some drawings with you as soon as you get settled. Okay. So this is a bit more of a lecture heavy day, so I wanted just activities to start us off. So we know that valence electrons are the most reactive electrons on the atom. That's our one thing we should definitely have seen from honors chem and then into now. So they're the only things that are going to be lost or gained in ionic bonding to achieve a noble gas electron configuration. It is not a noble gas though still, because it's still the atom itself with the same number of protons. So if you had to draw a Lewis dot structure, just simply identifying the type of, or how many valence electrons things have, sodium. How do you draw a Lewis dot structure for sodium? 1 dot, thank you. Fluorine, 7 dots. These dots represent valence electrons. Okay, so that's how you draw for an element, single elements, that just show an interaction, especially for ionic. What's the definition of an ionic bond? Or how does it form? Second? Transfer. So you will literally show, if you were trying to show the whole shebang happening, sodium donates, transfers that electron to chlorine. That ends up having, it leaves sodium with a charge of what? 1 plus. And sometimes we put brackets around it like that. But more specifically, we always put the bracket on the anion to show all of these electrons around it are its own now. So then we have fluorine with, saw on 8 dots first off, right? So we have octet here and a -1 charge because of the gain of electrons. So this is actually the Lewis dot structure for an ionic structure or an ionic bond. Okay? We don't show it actually bonding because it's not actually bonding, it's only attracting, right? That's the attraction between the positive, negative, opposite charges. So there's your one example for a Lewis for an ionic right now. Yeah, questions? This was a very simplistic example though. We did have one group, oh, they didn't mention this rule, but they thought they had in their PowerPoint. Whenever you're losing and gaining electrons, it always is to achieve a noble gas electron configuration. But hydrogen and helium are so teeny tiny, and beryllium even, we don't call it the octet rule, we call it the duet rule, because it only achieves a maximum of 2 valence electrons if it were to achieve that. My one group did, though, have isoelectric. Who was that, y'all's group? So they spoke of how some things are surrounding in a noble gas will gain or lose electrons to achieve that single noble gas electron configuration. So chlorine gains an electron, calcium loses 2 valence electrons, they become the electron configuration of argon, but are they argon? No, because what did not change? Thank you. So that's just a big misconception. So they're not argon because they have their own number of protons, which is their atomic number. Okay, so occasionally we'll have the duet rule occur, which is only going to be with things that are itty bitty. So like lithium will lose 1 electron, beryllium will lose 2 electrons. That's actually, or boron acts differently. It actually gets 6 electrons. There are many exceptions to the octet rule. I like to call it an octet suggestion, because it's not really a rule all the time. Okay? Give me a thumbs up when you're good to go. Questions on the slide? Information. Okay. We just did that. Perfect. Do you guys do the same thing for aluminum and oxygen? Aluminum and oxygen. You might have to draw additional elements or give some sort of subscript information. I don't want to leave you guys today, so just let me know when you need a break. Alright, so what are you guys drawing? Can we show the whole process? Tell me how many valence electrons aluminum has. 3. Okay. How many does oxygen have? Oops, 6. Okay. Can aluminum donate 3 electrons to oxygen? No. Okay, so I therefore need a different ratio. My previous example is a 1-to-1 because it was 1 electron transferring to make octet. It was perfect. But I can't accommodate that with a 1-to-1 relationship at this point. I must have how many aluminums?
2.
And how many oxygens? How do you know this? Anybody? Okay. Okay, because we know that aluminum and oxygen get together to form aluminum oxide, which is what formula? Al is a 3 plus, oxygen has a 2 minus, so we have Al2O3. We know this because we're like freaking AP chemistry students. We know that. We know the relationship already. But we know that aluminum loses 3 electrons. So how do you get this whole arrangement? You actually have numerous that are there transferring. So these 2 get transferred, and then these 2 electrons get transferred, and then these 2 electrons get transferred. So you see the relationship there. Now, you do not have to draw this humongous bit of information. You can go straight to the chase, which is what I think he was trying to tell me, but I wanted you to see the relationship was based on the ratio that does already exist, that you know exists. So aluminum, each of them have lost 3 electrons, right, total. But how many of them do I have? 2, as you can see in my picture here. So I'm just going to put a 2 subscript like that. And then oxygen, each oxygen has gained 2 electrons, gaining a negative 2 charge, but how many do I have of them? 3 of them. So that's kind of how you can indicate it with subscripts, incorporating it into the Lewis dot structure. Give me a thumbs up when you're good there. We do not frequently draw ionic Lewis dot structures. They are simply more about the fact that we know the charges exist, and then we can do charge products based off that and lattice energy. Oh, you guys just did this in your reading, so just make sure you put a circle or a star on the properties. You should definitely know all your properties. You guys can read that. You did your reading already this morning. You also already did some reading yesterday about the fact that Coulombic attraction comes back into play, when that lattice energy comes back into play. Because we've done this already, I'm going to skip some of this a little bit, okay? The only part that I feel is probably very specific is the magnitude portion. So if you're talking about the Coulombic attraction between a positive and negative charge, it's direct, the lattice energy, okay, the force of attraction is directly proportional to the magnitude of the charges, which is our charge product. Okay, so that's, what does directly proportional mean? As one increases, the other increases. And then inversely, so what's that mean? As one increases, the other decreases, inversely proportional to the size or the distance between those atoms. So that's a textbook definition basically of ionic attraction related to lattice energy and the strength of that structure. So I mentioned this in my, I think my ionic radius group. Tell me, which is soluble? Sodium fluoride or aluminum? Which is more soluble? Sodium fluoride or aluminum fluoride? Say again? Why? Okay, so this is more soluble, and we all know all first, alkali metals are generally all soluble no matter what they're paired with, because they have a small charge product, 1 plus and 1 minus. They don't have a strong attraction for each other. Water can attract them and rip them apart from each other because water is polar. Aluminum fluoride has a 3 plus charge product, or 3 absolute value charge product, whereas this only has 1. So this is a stronger attraction for each other. So water is less likely to overcome that attraction that those 2 ions have for each other. So it's less likely to be soluble in water. So there's a solubility relationship to the lattice energy. Thumbs up when you're ready. Trying to keep you alive here. Okay. Now, this was the stuff you did some reading with yesterday. So your graphs. Do you guys feel comfortable with what the reading said about this graph? I need a yay or nay. Okay, some people say nay. Okay, so let's look at this graph first. And they have this graph on every single exam, either multiple choice or free response, so it's important to see the differences here. So as these two this is an example of hydrogen. As hydrogen comes together, you can see it's closing the gap between them, and then basically they're overlapping each other here. Well, there's a difference in the bond length as that occurs. Well, there's this optimal bond length that does exist between the 2 hydrogen atoms. The optimum length is whatever the bottom peak represents, because that is the optimal length due to the interplay between the attractive forces that the protons have for the other's electrons, and they're not so close the nuclei are rejecting each other or repelling each other. because these are so close, the nuclei, the two positive nuclei are basically on top of each other. They're repelling quite a bit. That's a lot of unstable energy. So that has a very high potential energy. It's just very unstable. Well, separately, these two atoms have how many valence electrons does hydrogen have? Valence electrons. One valence electron. Separately, and also this other one has one valence electron. They're unstable in themselves because of their nature of their valence electrons. So what do they want to do to stabilize? They want to gain or lose electrons, right? They want a bond, but they're not ionic. They are not going to lose or gain. They're going to share. Okay, so when they share, they're going to basically combine that into a bond and call it two valence electrons. We've met the duet rule. We're in good shape. So now it's stable. But far apart, they're not bonded, but as they come closer together, they bond. That's why there's a minimum energy here, which is a nice stable bond. That bond has a length. The length is indicated on the x-axis right here. So that's a single bond between the hydrogens with a bond length of, I don't know, 20 picometers or something like that. So can you give me another diatomic molecule that might have a larger internuclear distance or bond length? Give me something else that would be larger. Oxygen, right? So oxygen maybe has a graph that looks like this, something like that. It's going to be farther over to the right because its internuclear axis is or distance is larger, simply because in itself, well, it has an extra energy level. It's larger than hydrogen in itself. What would be smaller than oxygen? Fluorine would be smaller. If you do your atomic radius, fluorine would be smaller. Diatomic fluorine would be smaller than oxygen. So maybe fluorine is here in black in the middle, something like that. So I only compared sizes and said the size differences occur here. There very well could be more of a dip here to show differences in potential energy, and that's going to come into play because you know how these bond a little bit already. So hydrogen's a single bond. How does oxygen bond? Double bond. Okay. Which of these bonds do you think is more stable? Oxygen, because it's stronger. Okay. So oxygen, because it's a double bond, it's a stronger bond. Stronger bonds are usually more stable. More stable, it's going to be a lower potential energy. That lower potential energy would be actually represented as a, let me get rid of some of this. And show you with the creative pen. Let's do happy faces. Okay, so oxygen would have a lower potential energy. There you go, best graph ever. Versus the hydrogen, simply because it's diatomic double bond nature. Okay.
Just observe that. Yes. Yeah. Can you do it shortly?
Thanks. Bye. All right. So there's our additional graph that gives you some information of the repulsive series here. Okay. I've already gone over all this. I've already gone over all this with you. We did all this stuff yesterday. I just didn't write it down. Now, this is the part that you guys wrote down, or that you expressed in your graph series yesterday. We had your individual balanced nuclear fictions. You saw some positives and negatives. Give me a heads up. I'm going to let you guys read that first and tell me what I need to explain. Because we talked about it yesterday.
So on the multiple choices question, the kind of EA actually is the
So occasionally, most of the time EA, electron affinity, was it a anion? Was it a metal or non-metal? Okay, for a non-metal, generally they're close to octet, right? So non-metals would love to have an additional electron. Okay, so if you give them an additional electron and it's a neutral, let's say chlorine, you give it one electron, it's going to be the octet, right? So if you're seeing that, do you think that's the stabilization process or building up energy process? Right, because it's getting octet, so that's going to release energy. That's an exothermic process. So where would you write an exothermic energy on your BCE? Yeah, so here, this example, you would write your EA here, whereas for sodium, if you were trying to get it an electron, heck no, it's got one electron, is it not on another one? You would write that would be an endothermic process, where it's electron affinity, and you'd write it on the reactant side. Thanks, Jacob. So this information has a lot to do with our trend stuff from earlier this week. Hello, sir. Come on in. All right. So in terms of heat of formation, definition of heat of formation one more time. Energy it takes to make 1 mole of a compound
From its elements
from its elements
in this
in the standard state. Okay, so in this case, why is this so large in this sodium example? Why is it so large and why is it negative? Let's do that. Is negative stabilizing or builds up energy? Okay, so this is a stable exothermic process. Overall, it's exothermic, and you guys saw the steps it took to do that. It was quite a number of them. But that's because sodium by itself could be more stable. It could have an additional electron, which it does over here in the sodium chloride bond that has been formed. Chlorine diatomic is actually not so bad. It's not that unstable because it's already a diatomic molecule that shares the valence electrons and octet, but it helps out sodium. Missing love. Process. I just kind of threw this up here for you guys. Like you did yesterday with your examples, goes from our initial bounces up through ionization energy, and then breaking of your diatomic bond, adding an electron. Where's what happened here? Oh, sublimation. Sorry, sublimation's down here. Prepping your sodium for ionization or ionic bonding, and then your chlorine takes on an additional electron. So that's an exothermic process. And then the heat of formation, lattice energy component, when you actually pull those together, it's going to be very, very stable, so it's releasing a lot of energy. And that whole process is going to be what creates that negative exothermic process overall, because of the octet that's been achieved by both parties, sodium and chlorine. But that's what I was referring to here as well. Okay? We can dive into that a little bit more, but tell me when you're feeling decent with this, so I can move on. Decent. It does relate back to our information related to trends a bit more than you probably think it does. So this all is our lattice energy calculation basis that we went through yesterday as well. We're going to read some more on this. And that was supposed to be stable, like a horse stable. Okay, thank you for laughing at that. All right, so these are the examples that we just went through. PDS we already went over. Okay, metallic bonding. You guys just reading on this morning? Thumbs up when you're good here, because we're going to reference it more on property basis later. We're not doing it drawings with these right now. The only thing I would say is if you want to include a drawing, you had this on your little card sort we just did. Blob, cation, 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 negatives around it to show the fact that they are not localized. What's the word for not localized? Delocalized. So the delocalized nature of that compared to this, what's this? The lattice structure, we have like an electron on the sodium, no electron on the, electron on the chlorine, no electron on the sodium. Electron on the chlorine, no electron on the sodium. So those are localized, meaning they have a specific location that they exist in. And the basically all the characteristics given by, are shown by metallic bonds are all stemming from these delocalized electrons. Malleability means you can flatten it onto the sheet. The electrons fill the spaces as like cracks form when you flatten things out. Ductility, same thing. Metal ions and the electrons can kind of slide past each other as you draw it out into a wire. The mobility of the electrons allow for electricity to be carried through, because electricity is just simply electrons moving, as well as heat. Heat comes through, and the mobility of the electrons allows for that transfer around to different parts of the solid very easily. So that's our electron, our information related to the properties of metals. Okay, so we did that. Okay, last part I'll do is drawing a couple Lewis dot structures with covalent, and we have about 30 minutes left, so we're doing really, really well here. This is an individual atom, right? Each of these are individual atoms. Whenever you form a bond, it's not actually a true structure. Lucas, be my other hydrogen, just because you just got here. Get up. Come over here with me. Okay. So I'm hydrogen. I have my electron. You got yours? Okay. So my electron's in my 1s orbital, right? And it's around me. That's just like doo-doo. Okay. So basically, we just scooch closer together. Okay. And then we're here. Okay. Yeah. And we're here. Yeah. Okay. We're just in the same orbital like now. We're just overlapping our orbitals. Okay. All right. And we're still here. All right. Good talk. Okay. So that's all it is. It's just locating. Their orbitals are overlapping each other, so their electrons are in shared space. So thanks for sharing my space. There's not actually a physical structure between them bonding them together. Okay. Can I move on? Okay. So these are those glue structures that you drew extensively in honors chem. The ones where you show the two electrons either physically come together as two electrons or two dots next to each other. I think it just takes too much work to draw those electrons like that, so I tend to draw as a line to show one line represents two electrons. So we call those bonding electrons, and the ones on the outside, what do we call those? Normally we don't call them non-bonding. How did you guys call them? Say again? Lone pairs. So many times you'll call these non-bonding electrons lone pairs. So those lone pairs of electrons, they're there because they probably originally belonged to that atom itself, right? So as chlorine comes together and the chlorine and other chlorine comes together, those lone pairs are just hanging out. The only two chlorine electrons that are merging are those two in the middle, which are now overlapping their orbitals to show some shared space, which we now call bonding electrons. They're just the ones that are involved in the bonding process. The lone pair of electrons, they're not involved in the bonding process. That's where the nomenclature is different like that. Yeah.
Do the same two electrons stay bonded, or do they kind of like switch in here?
They stay. According to one theory, there are two theories on bonding, and one of them says they stay. The other one says they don't. We know a lot, but we're not that smart as chemists. So it's called the hybridization theory, and so yes, it does. I agree more with that one. It makes more sense to me, basically. Okay, so those are our valid Lewis structures. The double bonds and single bonds, how many electrons is represented here? 4. So they're sharing 4 electrons, and the nitrogen is sharing 6 electrons. So what you should know about the differences between double, single, and triple is that one, well, how many electrons are there? 2, 4, and 6. And then sequentially, hydrogen bonds, not hydrogen bonds, a single bond, and I'm just using hydrogen as an example, is long and weak compared to the double bonded nature of something else like oxygen, or sequentially even shorter when we get to triple bonds. An example of that would be nitrogen. So the long ones are long and weak, our single ones are long and weak. The double bonds are shorter and stronger, and the triple bonds are even shorter and even stronger. Yeah.
So I didn't know when to add double bonds or like double bonds.
We're going to go through some examples. These are some that we've seen through maybe the bond association energy stuff we did a while back. So what you have to do is you have to count all the valence electrons available for bonding, redistribute them, and then rearrange them until you get a radial octet. I'm going to do some examples next, okay? All right, give me a thumbs up if I can move on. So a lot of basic review stuff, because I'm not spending as much time on basic review, because you guys did some of your reading for that. Let's draw before I get to bond polarity. Nope, hold on, pause. I'm going to talk about this first, and then we're going to draw a little bit. Bond polarity, Levi's group did a good job of talking about why electronegativity difference matter. So that's why it matters. It creates a bond that doesn't have an equal distribution of electrons. So, you know, Sean, let's be a bond today, okay? So, Sean, get over here, man. Sean is fluorine. Fluorine is greedy. Why? Okay, so most electronegative element on the periodic table, but why? Small means one valence electron and aka Zeph. Okay, so hi Zeph. Me, I'm going to be, I'll be iodine. Okay, I'll be iodine. So I only have one valence electron too, right? I mean, sorry, I have 7. I need one valence electron too, just like he does. But what's different about me? Why do I have a lower Zeph? Due to more orbitals blocking my positive nucleus from my valence shell. So you just said this shielding. I have a great shielding effect. He doesn't have. He's like with one shell, guys. He doesn't have any shielding. I have a lot of shielding. So do I want my valence electrons as much as he does? No. That's simply because I have a lower electronegativity than he does. So if we had to fight over the one that I have 7, he has 7. But if he wanted one of mine, I have to probably hold my hand. Okay. Oh, shake my hand. Okay. So we're trying to share electrons. He has one and I have one, but he's got a stronger pull for my electron. But we're still sharing, right? We're still holding hands. We're still sharing. But who's sharing more? Me. But we're still sharing. Still a covalent bond, but he's got the negative side of the bond, partial negative, because he's got more electrons surrounding him. I have less electrons surrounding me, so I have a partial positive. But not full-on positives and full-on negatives, because then that would be like a negative and a positive, and we'd be ionically bonding, and that for 2 nonmetals would not ionically bond. So there's a difference in the partial negative and partial positive, and full-on positive and a full-on negative. Full-on positives and negatives are ionics, partials are usually representing the unequal distribution of electrons. Okay, thank you, Fluorine. All right, so if you have an equal sharing of electrons, what would force it to be an equal sharing? I know, Jacob's got it. What property would allow for a bond to be equally sharing those electrons? I had the same number of valence electrons as he did. Thank you. So similar electronegativity would give us a likelihood of sharing equally, because neither one will pull the electron harder, or the shared electrons more so towards the self. So what would create an unequal shared likelihood of those covalent bonds? So yes, so a great difference in electronegativity. So one, they're still sharing, but one is pulling it closer due to its higher electronegativity value. So what that does create is an electron density. That's what we like to call it. An electron density greater around that more electronegative one, which we then say creates a dipole moment, which, Levi, will you explain that one more time?
Okay. It's a representation of how polar
Beautiful. Okay, so representation of how polar a bond is based on the differences in electronegativity. So you can see that this is a nonpolar bond, equal sharing, equal electron density around those 2 nuclei. This is a polar bond, which has the greater electron density around this guy, so that might be fluorine or something. We would then draw a dipole moment pointing like a linear line, putting an arrow towards the partial negative region, and a little hash mark, looks like a positive, on the partial positive region. And that little S, it's like I'm like too lazy to make an 8. That's what that is. It's called lowercase sigma. Lowercase sigma, yeah. And that right there is what we call partial. So that is showing a linear molecule with a partial positive and partial negative, aka a polar bond, or a polar molecule based on if that was the whole molecule or not. And of course, if we have an extreme difference in electronegativity, we have the full-on transfer of an electron. So we have a full negative charge and a full-on positive charge, which is an ionic situation. But it's a continuum. I think y'all's group for electronegativity, they put values up and it was like, if there's an electronegativity difference between 0 and 0.4 and 0.4 and 0.8 and 0.8 and 0.12 or something like that, it was distinguished as polar, nonpolar, and ionic. That is still a continuum, though. There are many factors that go into determining something's polar or nonpolar. So this is your general rule of thumb there, okay? Now, let's actually draw a structure, and this is according to the fact that valence electrons, when all atoms come together, all valence electrons are free game. They are fine to be involved in the bonding process. That is what a valence electron can do. But some are more likely than others to be involved. So, speaking of the continuum, I'm going to come right back to this. I'm going to go to drawing first. Okay, so we're going to draw some of these, okay? But how do we know the process of drawing? So I'm going to start with us drawing carbon tetrafluoride. So write CF4 down, carbon tetrafluoride. I'm going to walk through the process as I teach you the instructions. So carbon tetrafluoride, here we go. So your first step is to sum the valence electrons that are present in the entire structure. So carbon has how many valence electrons? 4. And fluorine has, so 4 times 7 of them. Good, because fluorine has 7 valence electrons, so this is in the 7th group. 4 of them. So total valence electrons, 32. Okay, second step. One of the atoms is likely to be a good sharer, meaning they're not so high in their electronegativity. They're able to stay in the middle of the atom and be the central atom. So usually it's going to have the lowest electronegativity because it's going to be the one that's likely to share with everybody. So which here is going to be our central atom? Carbon. I'm starting off with an easy example, okay? So carbon's going to go in the middle, and that's because it's carbon, first of all. If you have carbon, it is going to be in the middle. It loves forming 4 bonds. Why? It needs 4 electrons. It's like, please, somebody bond with me 4 times, because that's how it gets 4 extra valence electrons to seemingly have a noble gas electron configuration. If you have to choose the singleton, like if you don't have carbon, a single example within that structure itself will be the middle or the largest atom. That's kind of your priority list. I hope you're writing down some of your rules as we go. That's why I'm lingering so long. Okay, so secondarily, to your structure, you have to append every atom that's left. They're called ligands. And I'm going to say that for now as every atom, and you bond them to the atom, the central atom, with a single bond. So I'm drawing so far 4 bonds, and then fluorine, fluorine, fluorine. Because we put it on the central atom, we're going to have some bond polarity issues. We'll talk about what that means in a second, but we will see some distribution issues with our electrons. So, how many electrons have I used so far on my atom, on my molecule? 8. I've got 32 to work with, right? Currently, who already has octet? Carbon, 2, 4, 6, 8, is surrounded by 8 electrons. It is at octet. Who is not? Fluorine. So at this point, I am not bonding anything else to fluorine. I'm only going to add, so I'm going to call those what? Lone pairs, right? So 2, 4, 6, 8, good. 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 Okay? So now I've got octet on everybody, right? How many electrons are represented totally? 32. Check, I've met my limit. So the way I've arranged it is in pairs. Electrons occur in pairs, in lone pairs, because of the fact that orbitals hold 2 electrons. Okay? So I'm not bolding all those, you guys know they're there. Alright, so if I had, like, maybe I had 30 on my molecule so far, if I had 32, I have to append those extra 2 electrons to the central atom if it was needed, but that's only for special circumstances when the atoms are large enough to accommodate that. And that's usually going to be only for phosphorus, sulfur, fluorine, argon, and then anything below that. So basically, phosphorus, sulfur, chlorine, argon. That's at the end of what part of the periodic table? What orbitals? What p? 3p. What comes after 3p if you were to try to push electrons someplace else? There's not a fourth energy level in p, or in the third. There's not a fourth energy level if you only have a third energy level. Does that make sense? You don't have a fourth energy level. You're not going to push them to 4. You're going to push them to 3D. That is the beauty of why we go to 3D after 4s, because these have actually, I'm going to call them D pockets, because the 3D is what's coming soon, or is actually, it's there, it's available, it's just we don't have any electrons put in it. But if you had to shove electrons in it, you have the D block 3D specifically available to do that. Now, those are the only ones that can hold extra electrons. Okay, so if you have more, you stick them on the central. Yeah, let's actually figure out some more information about this now. Okay, how many ligands, the word I'm saying is ligand, how many ligands or attachments do you see on carbon? 4. You've got to memorize some of these geometries, and I have a whole sheet of them for you, but I want to make sure you pull in some of it from prior knowledge. Does anyone remember the structure with 4 legs? Tetrahedron, thank you. Or it's a tetrahedron, sorry, math, but a say again? Hedral 3D structure is what we call anything with 4 legs. Okay, so I have this molecule kit to show you this. We will build on Monday. I don't have a carbon. I don't have a carbon. It's not gonna work. Okay, so I will be carbon. Me, I'm carbon. Okay, leg, leg, leg. Okay, so this is a tetrahedron. What's the bond angle you're seeing between my arms? That's 90. That's 90. That's not at a right angle. It's not. Oh, it's really close. It's not 90. 120 would be if I had an equal, like, third, third, third. So I saw somebody wrote this down on their outline. A little over 100. 109.5. The bond angle here is 109.5. If you have 4 legs, we will work on memorizing these later. But 109.5 is the bond angle between these legs. Why does it not look like 109.5 here? It's a 2D structure. Like, how am I supposed to draw 109.5? It's a 2D structure, but truly these are molecules. They're 3D in nature. So what commonly, how it's kind of depicted, is like a carbon, 1 fluorine goes up, 1 fluorine comes out at an angle of 109.5. 1 comes out of the board and you fold in it with like a little thing, okay? And then 1 goes back behind the board and you dash it out. That's supposed to look 3D, right?
Sure.
Thank you. Okay, and this bond angle is 109.5. Okay, so we will get into a lot of these, but I want to give you a chance to draw a couple of these first. All right, now you guys draw formaldehyde, CH2O. Formaldehyde. And now probably red light carbon is like that. So draw it now. You're not drawing. You're not leaving. Let's go. Maybe you don't want to leave. It might be a bad threat. Savannah, did you grow up in a habit? No. So I'm going to harass you and make sure that you counted your electrons, because I know that you're going to try to cheat me out of counting your electrons, and then you'll find that you can't actually verify your results. So counted electrons, how many do you have? 12 valence electrons. Central, carbon, appended what? an oxygen, 2 hydrogens. And you always try to make it as symmetrical as possible because these are electrons and these are electrons and these are electrons. Those electrons don't want to be near each other. Don't put them all on the same side. Symmetrical. Okay, so that's how far I got. What else is next? Okay, I'm going to put 3 there for now. How many electrons have I used? 12. 2, 4, 6, 8, 10, 12. I'm done. Now, here's what you have to double check. Does everybody have octet?
No.
Who doesn't?
Carbon.
Carbon, 2, 4, 6. Okay, so that's what I want you to see. I wanted you to make a mistake. Why is hydrogen okay without lone pair? Duet rule is good. Oxygen has octet, but that's only 1. So instead of going, okay, greedy, oxygen, you've got 2 electrons by yourself. Why can't you just take those and share them? Yeah, share them as a double bond. That's what you do to make sure everybody has octet, and that's how you reflect on your structures. So I'm going to tell you one last thing before I wrap this up. So there's something called formal charge. You read about this? Formal charge? Okay. What you do is and I'll review this as warm-up tomorrow as well, but you compare the electrons that atom normally has, and you compare it to how many it has in the structure. So carbon normally has how many valence electrons? 4. Okay. Carbon normally has 4. And the way you count is you count every bond as 1 electron to carbon, because the other electron is basically like shared with oxygen, right? So if I count it, I count 1 electron, 1 electron, 1 electron, 1 electron. So how many do I have around carbon? 4. So 4 is what it should have. 4 is what it does have. It has a formal charge of 0. There's no additional electrons or lesser electrons than it should have. They're equivalent. Okay, what's the, how many electrons does hydrogen seemingly have here? 1, because they have the other half of the bond, right? Okay, so they show to have 1. How many does hydrogen have from the valence electron from the table? 1 valence electron. It seemingly has 1 formal charge of 0. Great. Okay, look at oxygen. How many electrons am I assigning it here? 6. 1, 2, 3, 4, and then the other half of those 5, 6. Seemingly 6 valence electrons are assigned, and then how many does it have on the periodic table? 6 valence electrons. This is a great example to show you all these formal charges on this Lewis dot structure are 0. That is the best arrangement those electrons will take on. Everything is stable, everything has octet, everything has a formal charge of 0, which is a desirable charge. These things are nonmetals, right? They don't want charges. They don't even want partial charges, which we'll get into a little bit more tomorrow. But this is a great structure because everything has a formal charge of 0. And we will actually work through working those more tomorrow, okay? So I just want to show you that one last example. Homework, ready? Flip open your packet. You see where it says reading guide, it's the 3rd page back, reading guide part 2. Yes, we're talking about today. So reading guide part 2, it says draw Lewis structures for the atoms or molecule below. That's all I want you to do. Do not check, you can't do resonance structures or formal charge yet because we have not gone over that in detail. But where it says for questions above, you're listening? Okay, for questions above, write down the molecular geometry. If you remember molecular geometries, try some of those shapes like tetrahedral, trigonal, planar, linear, bent. Try those. So you're only drawing and trying to predict shapes because you remember something from honors chem, like a champ. Okay? All right, last thing. We have a guest speaker coming tomorrow, if you saw it on my website. So it's Dr. Oya Keen, K-E-E-N, Keen. She's coming to talk about photocatalysis, basically we're applying light to clean up contaminants in water. So it's my last guest speaker for now from the light unit we just did. You see this reading? Okay. I would like for you to read and develop a couple of really, really good questions for her tomorrow, okay? Read and questions. I think that's a pretty light homework considering you guys did FRQs from yesterday.
I love getting Kim notifications right before
Yeah, I want you to do all 8 as much as you can. Put in the 5 for now, okay? Turn in the 5. Yeah. Yes. They're taking tests.
We never like added
Okay.
Two contract shoes
Okay.
problems last night.
We put those two in the box for you.
Okay, thanks.
automatically added.